Okay, now let's talk about the experiment itself. I'm just going to give you a general idea of what is going on, and that can help you with the with writing a report. I'm not going to go in each part in detail, especially that for part 2 you kind of have a video that helps, but I'm going to just give it general information to help you to understand what is going on in part 1 and part 3. So we had two schematic for low pass and high pass filter, right? This one out, bringing in. This one was high pass. This one was low pass. So what is it? In this case we have, in both cases we have an RC circuit. Your resistor and capacitor are in series with each other, right? The only difference between high pass and low pass circuit is that in the high pass, we are measuring the voltage on both sides of the resistor. On low pass, we are measuring the voltage on both sides of the capacitor. We have, if we just writing down to find out what would be, so we know that if you go through the circuit, the voltage on each point on one certain point should be, the change in the voltage should be 0. So we have V in, you go here, you go to V in, then go here, and there's going to be a capacitor, which is going to be minus VC, then go to the resistor minus VR, should be 0. Here is the same thing too, but it's just going to be V in minus VR minus VC goes to 0. So here your V out is actually your VR, and here your V out is actually your VC. What else do we know? You know V in is constant. You always change it to be 10 volt. So your VC plus VR is a constant. The sum of these two should be a constant, which means that if your VC increases, your VR decreases, right? Keep that in mind. And then we're going to talk about low pass and then get back to the high pass. So what we had was that VR plus VC equals to a constant, because your V in, you kept it constant. So now talk about the resistor. We know that the voltage in the resistor when it's charging, V equals V naught 1 minus E to the power T over tau. When you have an alternative current, what would be the range of the T that you can have? I'm gonna show the square signal again because it's easier to talk about. We know that if in this case the potential is positive, if you have something like this, when you get to this point, the positive and negative poles gonna change. So in that case, it's just gonna be this part. This is gonna be positive. This is gonna be negative, which means that only the half of the period the capacitor has the chance to charge. So your T can be only between 0 and half of the period. Okay. And usually when you do the measurement, it's the no, okay, I'm going to talk about that later. Okay. Now imagine that this is your input signal. You got the output signal of like this. You got to the plateau. Imagine this is like 5 hertz. What happens when you increase the frequency? What happens when you make it to the 10 hertz? Frequency equals to 1 over period, which means that when you are increasing the frequency, you are actually squeezing this wave, right? So at, for example, 10 hertz, you are gonna have okay, this is gonna be the shape of your input wave that you're gonna have. Okay. Which means that in this case, the capacitor has half of the time that it had before to charge. So in this case, it's not going to get fully charged. It's just going to get charged to this amount. That's the reason that what you're going to see is going to look like this. It's not going to be a plateau. It's just going to be and when you increase the frequency a lot, it looks like, so as you increase the frequency, you're going to change from a curve that goes and reach the plateau and goes down and reach the plateau to you're starting to chopping up, so it becomes more, it starts to get, looks like more like a triangle, and after like really high frequency, just like gets really noisy. As what you saw. Okay, so we noticed here that when we increase the voltage, when we increase the frequency, we lost some intensity for the higher frequency wave, right? Imagine that you have, okay, so that's it. That's the reason that, that is why the graph for like frequency, sorry, intensity versus frequency for low pass is gonna have a shape like this. Because you increase the frequency, lower the whole period, which means that you also like lower the half of the period, which means that you give less time to the capacitor to charge. Okay, now I mentioned that in the whole RC circuit, you have VR plus VC is equals to V input and which is gonna be a constant. So this is for your low pass. If you measure around on like two sides of the resistor, you're gonna have the high pass, right? So here for the low pass, here you have for the low pass, you have high, your VC is high, so your VR gonna be small. And then as your VC start to decrease, your VR starts to increase, although they should follow the same slope, so I should be careful about drawing it. Yes, this is gonna be your high pass. So now we know that why, like the high pass and low pass are opposite of each other. You have the same circuit for both of them. It depends on what do you measure for your V out. That's the only difference between these two. Now let's have a little bit of talking here about the graph itself. Imagine you're playing music. Music has a wide range of frequency. There are different instruments playing in different notes, and they're going to have a wide range of the frequencies all at the same time too, besides that. So imagine the intensity that you have for it. It's going to have this shape. I versus F. Then you are going to put a low pass. I'm going to show the low pass with the green bond here. Oh, and when we're talking about intensity, it's normalized, so it can have only value between 0 and 1 in this case. That's the reason in part 3 you actually have a graph V out over V in, because basically your V out is the amount of the signal that you get. But when you are dividing that by V in, you normalize that so the value can be only between 0 and 1. That is usually helpful for comparing different instruments with each other. It's also helpful to put it on a graph. You know, it's easier to like interpret that when it's between 0 and 1. You put a low pass. Imagine this is your low pass. And then you put a low pass, you're just gonna lose all the song that you had here. That's the reason that when you put a low pass on like a rock music or like a music that has opera is a good one too, because they have like lots of soprano singers that they go to the high pitch. Yeah, they can like break glasses. You suddenly feel that the songs become so muffled and dull because you lose all the high intensity. You can hear more the bass in the music, or like the low. You lose the high frequency and you can only hear the low frequency ones. One of the fun things that actually Daniel and Margaret did in their experiment, they increased both R and C really high. And what happens when you put R and C really high, I'm going to explain why is that happening, but you're actually moving the, you can call it the cutoff frequency. It's going to be the frequency that you start to lose the intensity. It brings it really low. And they were like, I don't know why we cannot hear the music. And then I was at their table and I was like, oh, what is the R and C that you're using? And they showed me, and I just like changed the R. I actually disconnected one of them. I disconnected R and the music came out loud. So there was no problem with the connection of the circuit. It was since the, actually if I want to be more accurate, it was like this. So they almost lost all the sound. They couldn't hear anything. Okay. Correspondingly, if you have a high pass, you're going to use the bass bar. Now let's talk about what happens if we increase R or C. So when R goes up or C goes up, your RC, which is equals to tau, goes up, right? Okay. What does it mean? Then I'm going to get back to our typical charging capacitor equation. Does everybody have problem with whiteboards? Archers? Okay, this is not working. Let's change the whiteboard marker. Okay. V equals V naught. Oops. 1 minus e to the t over tau. Okay. We have that. We are going to keep the same frequency, but we are going to change the RC. We are going to change the tau. So we're going to start with this figure that we have. Then we are going to increase the tau, see what happens. When we are increasing the tau, your period is the same, but your this ratio becomes smaller. So these terms become bigger. Then the whole coefficient that's going to multiply by V naught is going to become smaller. So let's put in an example. Imagine that we had V naught times 1 minus e to the minus 5. And then I made a mistake. I probably made a mistake here. Okay, we're gonna go with the example. Then I increase the okay, I was right, I guess. Yeah. Then we increase the tau, which means that like we make the tau, for example, 2 times bigger. We made R or C 2 times bigger, and now the tau is twice what it was. So your T over tau gonna be half of what it was. So that's going to be 1 minus e to the minus 2.5. So this term right now is actually larger because V naught, you can write it V naught 1 minus 1 over e to the 5. Or e to the 2.5. So what I'm saying that when you increase the tau, you actually make the coefficient smaller, make the power smaller. So your whole term that is the e to the power of that term becomes bigger. The whole coefficient that you have becomes smaller. So your V naught your V out gonna be smaller. So if I want to show it after we are increasing the tau, okay, I'm trying to, now you actually lost the intensity, which means that, yeah, so you lose the intensity in case of low pass when you are increasing tau. Let's show that on the graph. Consider this one to be your initial low pass. And imagine that we are talking about this frequency. So we noticed for the same frequency, if we increase the tau, you're going to lose more intensity, right? So it's like this, it looks like that the whole graph shifting to the left. Correspondingly, if you're increasing the tau, you're still like shifting the whole curve to the left, right? So if you have a high pass, that looks like the green one at the beginning. You're going to shift it all to the left, so it's going to look like this purple one here after increasing tau. Okay, that's it. I know that I hope it helps you with writing the report, and let me know if you have any question. Since I actually upload these videos late, I'm gonna, for the people who are watching this video again, you can have another extra night for deadline. You can actually submit it by Saturday night. I'll be okay. I'm not gonna take any point off for delay, but I want to get sure that you know what you did here and be able to explain that in your lab report. Okay. Sorry for my delay to uploading the video. Hope I could help. Ask me questions if you have. Bye-bye.